So yeah, it's nice to kind of virtually be back at A&M. I already missed Texas to some extent. I'm in California visiting Google this semester. Like you said, my background is that I'm a mathematician, but I got into theoretical questions in machine learning and specifically deep learning. But this will be a tutorial which is focused not on the theoretical side, but more just kind of to try to introduce what neural networks are and how they're used and so on. Okay, so please at any point ask me questions and tell me if you can't read what I'm writing. I think it's better to write by hand in this virtual kind of environment. Otherwise, you know, it's just too removed somehow personally. So let me just briefly list what the goals of the tutorial are. So I want to start by saying, what is a neural network? They often write NN for neural network. So deep learning as a subject is the use and study of neural networks. So they're practically synonymous. And I don't want to assume that everyone here already knows deep learning. And so I'm really going to start basically from first principles and try to explain what neural networks are. So the second thing I want to accomplish is I want to explain how neural networks are used in practice. So it's extremely important actually to understand how this goes, because really it's the details of how they're used in practice that allow us to kind of get a sense of what they might be doing and how to use them effectively. So in my mind, you know, I'm hoping that people come away from this tutorial with a kind of high level understanding of what a neural network is and what the basic steps are to use it. Yeah. Choices are going to be. So the third thing is I want to focus, and this will really be in the second half of the talk, on what kinds of kind of choices engineers have to make. Choices are made by engineers. So what I mean by this is that if you're a software engineer, or in general, engineer, and here's, I don't think I spelled it right, but you know what I mean. So, you know, if you're actually going to use a neural network, what do you have to think about? Because the truth is that although neural networks are extremely useful in practice, they're a little bit finicky. And so one has to be rather careful. And then the last thing I will sort of conclude with essentially is kind of a list of the main use cases. You know, what are the practical areas that neural networks are used for? And what are the kind of big failure modes or challenges to using neural networks? Okay, so these are my 4 goals essentially. All right, so let me start with part number 1. And to explain what neural networks are, I want to take a step back and remind you, or if you've never thought about this, tell you the paradigm of supervised learning. Okay, so supervised learning is one of the ways that people do machine learning, and it's often how neural networks are used. Sorry, can you their video, please? Because I hear reverberation.
Supervised learning.
Goes like this. It basically has 4 steps. Okay, supervised learning has 4 steps. So step 1 is data acquisition. So the fundamental setup for supervised learning is you assume that one way or the other, you get a data set. So you obtain a data set, and I will typically write script D for the data sets in this talk. So what is a data set? It's nothing more than a collection of inputs, comma, outputs that you would like to understand. Okay, so the key point here is that f is an unknown function. You don't have a formula for f, but you have examples of, for various inputs xk, what the correct value or maybe approximately correct value is for the function f. So here are some examples, or here's an example to keep in mind. So suppose that xk is an image that you take with your camera. Then maybe f of xk could be a binary function, and it just tells you if xk has a stop sign in it or not. Okay, so 1 if it has a stop sign, and 0 otherwise. Okay, you can imagine why this might be useful if you want to make a self-driving car. The car is going to have some kind of cameras on it, and it needs to be able to tell, you know, is there currently a stop sign in front of me? So it's also a good example because you see, humans are very good at computing this particular function f. If I show you a picture of a street, you will be with very high accuracy correct in saying, is there a stop sign or not on this street? But we don't actually fully understand how our brain does this computation. And so for a computer, the image xk is nothing more than a collection of pixel values. And so, it's unclear how to write a formula for f. You ask yourself, okay, let's look at the top left pixel of the image. What do you do with that pixel to determine whether or not there's a stop sign? What do you do with the middle pixels? What are the right correlations to look at? It's sort of unclear how this is supposed to work. So this is a good example where one can have a labeled data set, but it's not clear how to write a formula for it. And in fact, the goal of supervised learning and the goal of neural networks in this context is to learn a good approximation to the function f. Okay, so that's how neural networks are going to be used. Okay, so going back to supervised learning, the second step in supervised learning is what you might call model selection. Different communities actually call this different things, but I'll call it model selection here. So model selection just says, well, I'm going to assume that f has a certain form or can be approximated by a function of a certain form. So you choose a model class. So it's a class of mappings from an input x to the outputs of a model. So I'll write script m in this part of the talk, and that reads x and then semicolon theta. So the notation is that theta is some vector of trainable parameters. Vector of parameters. Okay, so a common example might be that m of x and theta is just a linear function, a1 x1 plus dot 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 plus an xn. So x is a vector, and then theta in this context is just the vector of the AIs. Okay, so we basically say, all right, well, we need some way of trying to parameterize the space of guesses we're going to search over. And the vector of parameters theta basically tells you how to parameterize this space, whereas the choice of model tells you the form of the computation. Okay, so that's step 2. Step 3 is you say, okay, now that I fixed the form of the computation, I want to try to find a good setting of the parameters. Okay, so this is what you might call optimization. Okay, so optimization consists one way or the other. It's not a priori clear how to do this, but you somehow want to use the data set, which are examples of the correct values you'd like to interpolate, to obtain a good setting of parameters. So you want to obtain a setting of parameters, I'll call it theta star, such that the following essentially holds. So on your training set, the outputs you have are pretty close to the outputs that your model gives you with this setting of trainable parameters. Okay, so that's the goal. You have some examples, a data set D, you have a model class, and then you would like to choose a value of the vector of trainable parameters that at least does a good job of kind of interpolating the examples you have. So an example you're all familiar with is you might set theta star by linear regression. Okay, if you have a linear model or something like a linear model. In other settings, the optimization is going to be more complicated, and indeed in the neural network setting, it's not going to be linear regression, but that's what I mean by optimization. Okay, so then the last step, so the data set is only a proxy for the values of the function f. You already know the values of f on the data set. So your goal isn't to just memorize the collection of inputs xk and outputs f of xk. Your goal is to actually extrapolate to new data. So the last step, which is very important, is what you might call testing. So testing just means you see how well you do on data you haven't seen. See how well theta star, this setting of parameters you learned, performs on unseen data. Unseen data, and what this means specifically is you take a new input x and you ask, is it true that f of x is approximately equal to m of x theta star? Okay, so I'll write it this way. And the point is that the input X that you check on is one that was not in your training set. You know, maybe you have 1,000 examples of stop signs, but you actually take a new picture of a street and it may or may not have a stop sign, and you would like the algorithm to actually correctly output, at least with high probability, a 1 or a 0 in this case. Okay, so this is the general paradigm in which I want to introduce neural networks. And in the context of these steps, you know, neural networks are really kind of in these 2 steps. So step number 3 and really step number 2. In essence, neural networks are just a choice of model class that you're going to use, and you could in principle use them for any supervised learning problem you want. I'll get into a little bit what kinds of supervised learning problems neural networks are actually good at solving. But okay, so for now, that's my basic introduction to neural networks. And so what I want to say now is that, in essence, neural networks are kind of unusual in a couple of senses. So I want to just list these senses here very briefly, and then I'm going to go on and actually define a neural network and give you some examples, and then tell you a little bit about the inner workings of how these examples are supposed to work. Okay, so salient features, let me call it that, salient features. There are many salient features, and obviously I can't cover all of them, but just from the point of view both of the theory and the practice of neural networks. What are some of their important properties? Okay, property number 1 is that the input dimension, i.e. the number of components that X has, is often very, very large. So they do well for reasons that are not fully understood theoretically, but empirically, they do extremely well in high dimensional data. You know, the input dimension might be on the order of 100, or might be on the order of, you know, 1 million. That's not impossible to have neural networks with these kind of input dimensions. And so, you know, traditionally in the machine learning world, people worried about things like the curse of dimensionality, where really high dimensional inputs are hard to learn, but something about neural networks helps them overcome it, at least in some cases. So this is one kind of aspect. Another salient feature is that the number of parameters, typically in a neural network, so the number of thetas that you have, you know, this vector theta, in the linear case, for example, describe the coefficients of the linear function. But in a neural network, we'll see they describe something called weights and biases. So typically the number of parameters that you train is actually way bigger than the number of data points that you have. And they're both very, very large. So you might say that you're in the big data regime, because typically neural networks are very data hungry. So you might have millions, hundreds of millions, even training examples, depending on the setting. But very often you have even more parameters than data points. And so somehow neural networks aren't scared off by this, although traditional statistical learning theory sometimes warns against this. Okay, so that's 2 salient features, and then maybe let me conclude with the last one, and that's that neural networks both interpolate. That means they can often just exactly fit your data. There's no error on your data set, and simultaneously extrapolate to new data points. Okay, this is an unusual feature among such models, and I won't get too much into it, but I think it's just important to know that, in fact, in practice, very often the way one makes sure that the neural network one is using is actually working right is you actually interpolate a big data set that gives you a reasonable check that you're doing well, and then you train the neural network on the data set you want, and you actually use it to make new predictions. Okay, so I want to move on, but I don't want to skip too much. So if there's a question at this point, I'm happy to take a question about any of this. I hope it's relatively clear, but if it's not, please tell me. And if there are no questions, I'll go on to defining what a neural network is and trying to draw some pictures and telling you what kinds of model classes they represent.
Question.
Hi, can I ask a question? Hello?
Sorry, I think I was muted for a second. Yeah, absolutely. Please ask a question.
Hi, Boris. This is Saravanan. We met some time ago. When you said the number of parameters exceeds the number of data, just from information theory perspective, are there some constraints on the parameters that the amount of information is less
So the short answer is no, and the long answer is yes. So neural networks, as I'll explain, are optimized in a very particular way, which implicitly makes them learn simpler functions than they are in theory capable of representing. So if you think about the usual kind of issues where you have more parameters than data points and you're worried about overfitting, overfitting is basically a worst case phenomenon. But what happens is because neural networks are optimized in essentially a kind of very simple-minded, greedy way, they typically start their lives as rather simple functions, and you can prove theorems about that, in fact, where there's a kind of bias towards having way less information in the parameters than in the data points at the start of training. And then you optimize them to quickly get to a reasonable solution. And so just intuitively, you don't learn too much more information than you started with. But okay, that's somewhat hand-wavy, and I wasn't planning on covering that, but if you're interested, I can send you some literature on exactly what people know. But the fact is we don't fully understand why it should be possible to kind of have all these properties satisfied, that you perfectly fit, you perfectly extrapolate, and you have more parameters than data points. That should ring some bells as like alarms. So it's a fair question, and my answer is only partial like that.
New question?
Yep.
When you speak of dimension, do you mean the dimension of X? So in your example, the number of pixels in the image?
Yeah, correct. When I say input dimension, I mean the dimension of the vector that you feed into the neural network or into the model that it then goes about processing. It's also high dimensional in the sense that the number of parameters it has, that vector theta, is high dimensional as well, but that's not what I meant when I made that comment.
Another question?
Yep.
So when you say extrapolate, my understanding of neural nets is that when you train them, it's a good function fitter for the scope of the data that you train. And so when you say extrapolate, do you mean outside the statistical scope of the data that you're feeding?
Beyond the data set. You have some consistent function f you're sampling. And I mean, the neural networks not only learn the values at the data points, but they also do a good job of, okay, typically, often, if you train hard enough and so on, they do a good job of returning the value of f away from the data points. So for an x it's never seen before. That's what I mean. Certainly if you change f dramatically, it's not going to do well at all.
No, sorry.
So that's the intuition, and we don't fully understand exactly what's going on. That's the truth of the matter.
That is more interpolate, right? I mean, between points, I see that it can do a good job, but outside.
Well, okay, I'd rather not answer that question because it's semantics. And we don't know what's happening, so I don't have a precise disambiguation. Okay, so I use those words, people use them, but you can feel free to just ignore them. They're just kind of intuition.
Perfect, thank you.
Yeah. Okay, I think I should probably go on, so I'll stop a couple more times for questions. So let me now say what a neural network actually is. I wanted to just motivate them a bit, but I haven't told you much about them. So the purpose here is to define neural networks, and don't worry, I won't do it in too incredibly rigorous of a way, although what I say can be made into a perfectly rigorous definition. So the basic point is the following, that neural networks are built out of very simple computational units called neurons. Built of neurons. Okay, so maybe I should just say a word about this. Neural networks were originally introduced, in the late 40s, early 50s. So they've been around for a long time. And a neuron was supposed to be a simple model, but not a particularly accurate model for the computation done by a neuron in the brain. Okay, so here's the computation done by a neuron. You start with a vector x, which has components x1 up to xn. Those are the inputs to the model. And you output the value of a neuron, I'll write it z of x comma theta. So what kind of function is this? Well, it's a fixed nonlinear function sigma of a scalar b plus the dot product of the vector x with the vector w. So let me kind of disambiguate what's supposed to be going on. So first of all, the vector of trainable parameters here, or vector of parameters theta, is the bias B and the values of these scalars, W1 up to Wn. And the names for these things are the following. I've already kind of used them. So B is the bias, and these W are called the weights. Again, it's very useful. In fact, I'll draw lots of pictures to have a visualization of what a neuron does. So here it is. So you draw the inputs as nodes. So X1, X2, down to Xn. Every node carries a scalar. And then this node will be the computation done by the neuron. So what you do is you link the inputs with the neuron, and on each of these edges, you draw the value of the weight, W1 up to Wn. Then over the neuron, you draw the bias B, and the neuron outputs sigma of B plus W dot X as vectors. Okay, that's the computation done by the neuron. So you might call this integrate and fire. That's the catchword that people sometimes use in the neuroscience world. And the intuition is just the following, that each one of these X1, X2 down to Xn can be thought of as the output of an upstream neuron, which has done some computation. So this neuron says, okay, I'm going to take a linear superposition of the signals that I see with synaptic strengths given by my vector W. And then I'm going to output a fixed nonlinear function sigma of that signal. So again, to emphasize, this sigma is a fixed nonlinear, typically nonlinear function. And I'll give you some examples in a moment of what sigma can be, but that's what a single neuron does. Okay, that's the computational model that people invented way back in the day for a neuron. But now I can tell you what a neural network is. And I'll write definition, but in quotes, because it's not completely precise, but still. So a neural network is nothing more than a collection of neurons and a way of wiring them together. So is a collection of neurons together with a wiring diagram. So let me draw a picture. So for instance, you might have two input nodes to this network. And so these are distinguished nodes, and this is my vector X that I'm going to input. Then I have a bunch of neurons, and I'll draw them any which way I please. And I'm going to have some output node. So this is going to be N of X and theta. That's going to be my output. And then I'm going to have connections between various nodes. And in principle, the connections can be absolutely arbitrary. So this is a fine example of a neural network. And the way you think about this is every blue edge has a weight attached to it. And then every neuron has its own bias and its own nonlinear function sigma. And you simply compute the output N of X and theta. You compute this thing by recursively going through the network. That's one way you can think of it. Or you can go forward. You start with the vector X and you compute the output of this neuron. And you compute the output of this neuron and you compute the output of this neuron once you know this neuron, and so on. And you can go forwards through the network and finally get out the output N. Okay, so that's what a neural network looks like. And theta consists of the vector of all B's and W's. So by all, I mean the weights and the bias of every neuron in the network. That's the full vector of trainable parameters. And then this wiring diagram that I refer to, the particular way in which I connect the neurons together. So this has a particular name. This is called the architecture of the network. Okay, so when people say, I want to use a neural network, what they mean is they're going to fix an architecture, in other words, a wiring diagram for neurons. And then they're going to have a vector of trainable parameters theta that they're going to try to adjust to their data set. That's precisely what the neural network is doing. All right, so I want to now kind of bring this down to earth because it seems very abstract, but I'd like to just give one simple example of a function that you can compute using a neural network. So my example is going to be like this. My nonlinear function at all my neurons is going to be what people call the rectified linear unit, ReLU. And that's just a very fancy name for a very simple-minded function, just the maximum of 0 and t. Okay, this is a nice nonlinear function. If your input is negative, you zero it out. If it's positive, you keep it. And I'm going to make the following network. So it's going to have a single scalar input x, and it's going to have 3 neurons. So it's going to have neurons here, and it's going to have a neuron here. And then my weights and biases are going to be as follows. Okay, so all of the neurons are going to compute this same nonlinear function sigma. So I'm not going to specify it, but my weights and biases look like this. It's 1, 1, 0, minus a half, 2, negative 4, 0. Okay, so let's trace through what this does. So let's focus first on this top neuron. What is the computation being done by it? Well, it computes sigma of 1 times x plus 0, right? 0 is the bias. I have a scalar input x, and I multiply it by the weight vector 1, which is also scalar. This neuron down here similarly computes 1 times x minus a half. And the final output neuron computes sigma of, okay, so what does it do? It takes 2 times the output of this neuron up here. So 2 sigma of x. And then it subtracts from it 4 sigma of x minus a half. Okay, that's the computation done by the network. That's what it outputs. That's the function that I'm trying to draw. So as you can see, this might seem crazy because, okay, I wrote out the function, but you might ask yourself, what in the world is this function? Well, funny you should ask. I will show you. So I claim that this one is easy to draw out, and there will be 3 interesting inputs. So this is x space, 0, 1, 1/2, and this is the x-axis. So let's do this. So if x is negative, so if you're on the left-hand side of 0, then this neuron here is off in the sense that sigma of x is just 0. And similarly, this neuron down here is off because sigma of x minus a half is also 0. So the function here is just identically 0. Just get the 0 function. Okay, so now when x is between 0 and a half, what do we see? We see that this top neuron is on because sigma of x is x is positive, but this bottom neuron is still off because x minus a half is negative. And so we get a linear function, which is simply going to go with slope 2 up to the value 1. Okay, so now when x is between a half and 1, both of these neurons are on, right? You get sigma of x, that's just x in that case. Sigma of x minus a half is x minus a half. And then the output, notice, combines them with coefficients 2 and negative 4. So you get something with slope negative 2. So you go back down to 1 with slope negative 2. And then when x is bigger than 1, the final neuron is off. In other words, this final sigma has a negative argument and therefore zeroes everything out. And you simply get the triangle function. Okay, so this is a famous function that comes up in signal processing, for example. Sometimes it's called the hat function or the triangle function. And what I want to point out, just as a point of intuition, is that each neuron in this network causes one of these breakpoints in the graph of the function. And so this nonlinearity that I chose, the ReLU, is the most popular nonlinearity used in practice. So if you are interested in computer vision or if you're interested in natural language processing, a lot of the time you're just going to be using the ReLU. And the ReLU makes neural networks that compute piecewise linear functions. And the point is that ReLUs can turn on and off, and they create different pieces to your piecewise linear function. That's sort of the intuitive way of thinking about it. But you see, even in this simple example, it was a difficult matter to translate from the weights and biases of the network to the function you actually compute. And that's always true. So this is a fundamental difficulty in thinking about neural networks, that the way a computer likes to think about a neural network is just as a vector of weights and biases that specify its calculation. But for a human, we need something like the graph of the function. We need qualitative properties. And they're not so easy to translate back and forth between. Okay, so that's the most technical I'm going to get. That's my example of a function computed by a neural network. So my plan is basically to now tie this back into the supervised learning framework. Okay, and then I'll stop again and I'll try to take some questions. So let me show one more important thing. Sorry, let me scoot back here and just make a remark. So in the definition of a neural network, this wiring diagram, the wires that connect the different neurons, was in principle allowed to be absolutely arbitrary. But in practice, when you use neural networks, you almost always use rather structured wiring diagrams. So I want to make a remark about that because it's so important. Okay, so the way I'll phrase it is that in practice, neural networks have layers. That's what they're called. And rather than trying to give a formal definition, I'll just show it by a picture. That's the easiest way. So a layered neural network is just organized into computations that proceed one layer at a time. So let me try to illustrate that. So maybe these are the neurons in the network. So here's my input. Here's going to be my output. And you should read the picture from left to right. And then a layered network has a wiring diagram where you have a collection of neurons. So these neurons in particular, these are neurons in the first layer. And they're in the same layer because they only take in as inputs things from the previous layer. And the previous layer here is the input. Okay, so then you can continue your wiring diagram. Maybe it looks like this. And then you arrive at the second layer. Actually, let me put it in blue. So this is the second layer. And then finally, maybe everything is connected to the output node. Okay, so this would be a network that is divided up into layers. And it's a certain kind of wiring diagram. So, okay. And we'll sort of return to what the point of these layers is, but let me just tell you some nomenclature. Okay, so the width of a layer, so I'll draw this in red, this has width 3. So that's the dimension or the number of neurons in the layer. So if you hear people say, oh, my network has width 100, or I have a wide neural network, what they mean is that the dimension of the intermediate representation that you get, right? You start with X, and then it maps to some representation, which is the first layer version of X. And now you start with a 2-dimensional vector, and you ended with a 3-dimensional vector. And that's because the first layer has width 3. And then you map from X1 to X2, and this is another nonlinear transformation of your original X. And again, it's a 3-dimensional representation. And then finally, you get the output, n of X. Okay, so that's what the width is. And then the depth is what people call the number of layers. So when people say the word deep learning, what they practically mean is that they have a neural network that has a lot of layers. And a lot here might mean 5, it might mean 10, it might mean 100. It generally doesn't mean 1,000. I don't think there are too many networks in practice that have depth 1,000. But that's why people invented a new word, partly because it sounds cool, but partly because they wanted to emphasize that in past life, neural networks typically were shallow. They only had one layer. But now the observation empirically is that deep neural networks, or neural networks with many layers, perform really well. Okay, and in some sense, the most basic intuition that I want to highlight here is that you should think of layers as being hierarchical representations. Hierarchical representations, right? So you can say it this way: you start with an input X, that's my vector I start with, and in the first layer, I extract a nonlinear function of X. That's like a nonlinear change of variables. And that's my first extraction of interesting features from X. So then you say, okay, well, what does the second layer do? Well, the second layer is a nonlinear transformation built up out of the first nonlinear approximation. And that's why I use the word hierarchical here. Essentially, the layers build on top of each other in a compositional way. Okay, that's a basic intuition that people have. And so I wanted to at least spell that out. I anticipate that some people might have questions, but just give me a couple more minutes. I want to write out what the steps of supervised learning look like for neural networks now, and then I will pause and I will try to take the questions and have some kind of discussion about what's going on. Okay, so I want to now go back and tell you how are neural networks used for supervised learning. So I call this typical use. Again, let me emphasize that neural networks are not only used for supervised learning, but just for the purposes of this tutorial, that's what I'm going to focus on. Okay, so the typical use, again, has a number of steps. So the first step is unchanged, and remember that that one was data acquisition. Right, so that just meant I have some kind of data set that I'm given. So I have a data set D, of inputs xk and outputs f of xk. All right, so just to go back to the question that was asked before, these vectors xk are elements of some Euclidean space, they're vectors of dimension n0. And what I said before is that typically n0 is quite large, although not always. So that's what it means to have high dimensional data, at least in my sense here. Okay, so now remember step 2 was supposed to be model selection, but here it has a slightly different name when we're only using neural networks. It's called architecture selection. Right, so architecture selection means exactly what you think it means. It means you choose the wiring diagram. Okay, so you choose actually the sigmas, the nonlinear functions at each neuron, the wiring diagram for your network, and things like the depth and width, which are determined also by the wiring diagram. So if you have a layered network, you can say my first layer has width 100, my second layer has width 20, and so on. Okay, so these things basically put you in the context where you now know what the output of your neural network looks like as a function of the input, but you haven't yet specified the vector of trainable parameters, right? You've only specified the model class. And so the way I like to think about it is a little silly, but I will draw the picture anyway. So I think of the space of functions that a neural network can compute with a fixed wiring diagram. It's some interesting nonlinear manifold of functions. So every point in this manifold is just given by the function computed by a particular value of trainable parameters theta. Okay, so n again is my neural network. So every point here is some value of theta. And the goal is to find a good setting of parameters theta to fit your data set. And so the way you do that is you split optimization into 2 steps. So step number 1 is you randomly initialize or choose the vector theta. So remember, this is just the vector of all the weights and biases in the network. And the way I think about it in this picture is I just have some starting point theta 0 for optimization. Now, theta 0 doesn't have anything yet to do with the data. So of course, the particular function I start at doesn't tell me anything about the data set. But I hope that somewhere, maybe over here, there's a good value of theta star, which does a good job of interpolating my data. And my goal is to try to find it. And I find it in the silliest way possible. Okay, so this is step 3 prime. This is the second step of optimization. I optimize the theta vector by gradient descent. And I'll say more what kind of gradient descent later, on some kind of empirical loss. So the loss function D that you're trying to minimize, so the script D down below is the data set, is given as follows. You sum over the data set, or maybe it's better to say you average over the data set, how well you're doing at each data point. Okay, so for example, you can think of little l as being just the squared error. That's one example that you could have. Okay, so again, the idea is on each point in your data set, you have a notion of how well you're doing. When the loss is small, when the error is small, you're doing well. And your goal is to minimize this total loss, which is how well you're doing on your data set overall. And it's called an empirical loss because it's an empirical average over your data set. That's what I've written. Okay, so you have to choose a loss function like this. And then step 4 is the same. Okay, so step 4 was you have to test, which is supposed to mean you draw new points x, comma f of x, that the computer hasn't seen yet, and you check whether you've actually done well, whether your neural network at the trainable parameters you found is approximately equal to f of x. And again, you start here at theta 0 and you do some kind of local search, and maybe you go in the bad direction for a while, and then you come back, but hopefully, ultimately, you find theta 0. That's the cartoon picture of what you hope happens. Or sorry, not theta 0, but theta star, the good setting of parameters. And good here means ultimately this, right? This is the ultimate goal of training any model on any data set. Okay, so let me just conclude this section and take questions by saying that empirically, I've kind of already mentioned this, but it's so important I'll say it again, deeper is better with an asterisk. What I mean is that when you're doing your architecture selection, when you're figuring out what kind of wiring diagram to use, having more layers seems to help with actually generalizing to data you haven't seen. In other words, doing well on new inputs X. So why this is not completely understood theoretically, but it's an empirical fact with an asterisk, which I'll get into in the second half of the talk, that deeper networks are also often harder to train. So in the second part of the tutorial, I'm going to try to explain what are some of the basic principles for choosing your architecture and how to think about the trade-offs that you're making. So that's kind of going to be the more specialized goal. But again, let me stop now. I assume that people have questions. I'm happy to take questions on any of it. And then we can go from there.
So I have a question. This is Alan McIntosh, Cyclotron Institute, A&M. What about different structures of networks that don't fit this simple first layer, second layer scheme? First thing I can imagine is a connection between first layer directly to a third, but maybe more interestingly, what about feedback loops, positive or negative feedback?
Yeah, so that's a great question, and I've definitely oversimplified things. So we will see in the second part of the tutorial things called residual networks, in which indeed you skip layers. And that's very popular in practice. And it's still highly structured like this, but you'll see that the skip connections are important. So the answer to the second part of your question about whether you can have a feedback loop is ultimately no. In the following sense, you can build in a feedback loop, but then when you actually want to compute the derivative, when you want to compute the derivative of the output with respect to the input, because you're going to optimize by gradient descent, what you have to do is you just have to do what people do in belief propagation, basically. You unfold your kind of network that has a cycle in it. You can think of each of these wires as having a direction, right? It's telling me that there are no loops. And you're asking, what if I built in a loop like this? I'll put it in a different color. You're asking, what if I did that? Well, it turns out to be painful to actually compute the gradient. So what you do is you just say, okay, I'm going to give myself 10 iterations of that loop, and I will draw an equivalent wiring diagram, which has no loops in it, but has more neurons effectively in it. And then I'm going to use that to actually compute the derivative. So I'll get into that a little bit, but the name for this is what people call back propagation. It turns out that there's an efficient algorithm for calculating the derivative of this loss function L with respect to any of the trainable parameters in the network. But it's only efficient if you don't have any loops. It doesn't actually terminate if there are loops. So it's important, and there's a whole class of networks called recurrent neural networks, which are used for a number of applications. And certainly, partly you're saying that in the brain, obviously we have feedback loops, and that's super important. And that goes back to what I said before, that neural networks are not a great approximation of what happens in the brain at all. So some things people do in the neural network world are biologically inspired, but continuous time networks with feedback loops are a totally different beast. And as far as I know, they're just, not really kind of optimized or thought about in the same way as these artificial neural networks, which are what people might call feed forward. There's no cycles in the graph. So I hope that's somehow helpful. If you're interested, you can send me an email and I can send you some references that kind of explain this point more. Other questions or comments?
Boris, it's Alex Brinson. You mentioned gradient descent.
Yeah.
So in general, it's kind of a greedy, right? So did people look on other techniques?
The short answer is no. Well, okay. The long answer is yes, and the short answer is no. So the long answer is people have tried for a long time to find alternate ways to optimize neural networks that are not gradient based. But we have not yet, as far as I know, ever found an effective way to do the optimization. It just so happens that first order methods for neural networks are incredibly efficient to implement in practice. You know, I said that the number of parameters is large, but I mean really huge. You know, it can be like, in some networks, it can be hundreds of billions of parameters. And so you have to have an incredibly effective numerical scheme to do your optimization if you're going to adjust every parameter, you know, 1 billion times or 1 million times, right? So somehow we haven't found good search algorithms in these extremely high dimensional spaces that are not local and greedy. And this gets back to one of the questions that was asked at the very beginning. So I'll say a little bit about this, but unfortunately not much, although it's a beautiful topic. It turns out that greedy search, at least this is people's current understanding, gradient-based search, is incredibly important for encouraging the network to learn a simple function. Basically, you know, in your random initialization, the way you set it up is you set it up so that you typically start with a very simple function. And then you try to go as quickly as possible, i.e. by some kind of greedy first order method, to the nearest simple function that actually interpolates your data. And if you didn't do that, you might learn a bad setting of parameters theta star, which perfectly interpolates your data. There should be no problem with that in principle, because there are way more parameters than data points, but does extremely poorly on new data. So you don't generalize, and if you can't generalize, then your model is kind of useless. You know, you just memorize the data set. So it's complicated and we don't fully understand. But you know, I think it would be a major breakthrough in the field if someone could come up with an efficient and effective alternate optimization scheme that didn't involve computing so many gradients. But as far as I know, nothing like that exists at the moment.
Thank you.
Yeah.
So Boris, Anusha here. I have a quick question. So I was wondering how much is known about the settings where the input of the activation function, sigma, if you will, is not assumed to be just a fine combination of the coordinates of x.
Yeah, okay, so there's two senses in which you might ask what is known, like the word known, right? So there's the empirical sense. People have certainly tried interesting things. You know, you take not just an affine combination, but you take several affine combinations and then you take their maximum. That's called max out. That's something people have tried. You know, you just, instead of taking an affine combination, maybe each neuron should be vector valued. It's some interesting, you know, two-dimensional nonlinear function rather than just a scalar nonlinear function. And people have tried and they haven't found anything that works. So, you know, it's sort of this frustrating thing. There's so much freedom in principle once you start thinking about nonlinear models and you ask why this particular model? And the answer is that, well, it works in practice, so that's why people use it. But if there were a way that actually has, you know, is more rich and yet is still tractable in optimization and can do well in practice, I think, again, people would be extremely interested. But as far as I know, this kind of thing is simply not available at the moment, although people have tried. Yeah. So if you have an idea, you know, you should write a paper about it and you can become famous.
Sure. All right, thank you.
For questions? Okay, seems like there are no more questions. So I think it was advertised that the tutorial would be 2 parts with a 10-minute break. So I think this is a perfect time, to take a break. So let's do that. And then we'll come back and I'll start talking about some of the guts about how to think about architecture selection, how to think about initialization, how to think about optimization for neural networks. Okay, so let me start this second part of the tutorial by, now that you hopefully have some sense of what a neural network is, and like at a very high level, how they're used, you know, architecture selection, optimization, and so on. Let me just give you an overview of the main use cases in practice. Okay, so the main uses of neural networks basically fall into 3 categories. And I'll come back to this actually at the end. But I think it's kind of nice to think about the various things people can do in practice. Okay, so the first use case is natural language processing, NLP. And in NLP, your inputs always have something to do with language. You know, your task might be to translate from one language to another, to translate from text to speech or speech to text, or, you know, to generate the script for a movie, something about natural language. So maybe a typical input XK could be a sentence, you know, the cat is big. Okay, that's not a very sophisticated sentence. And, but that's the input to your network. So of course, this is not literally the input to your network because the input needs to be a vector. And so I'll put an asterisk here, and I wish I could talk about this. This is one of my favorite things about neural networks, but alas, I don't have time. It's a really beautiful question, how to turn a sentence into a vector. But okay, that's a discussion for another time. So f of xk might be the translation of this sentence into French. You know, let's see how rusty my French is. Le chat est grand. I think that's one, at least, you know, second grade level translation. So somehow you want to go from one vector to another vector, or maybe more precisely from a vector xk to a probability distribution over vectors of outputs in French. Okay, so that's roughly how NLP tasks work. And, you know, you use these tasks, or at least I use these tasks all the time. So Google Translate, you know, under the hood, has been revamped in the last couple of years to use neural networks as the main core for the translation engine. Things like Siri, you know, if you use your Siri on your phone for anything, the core is natural language processing, and in fact, neural network-based natural language processing. Any chatbots that you interact with, you know, hate them or love them, but they are very often done using neural networks these days. Basically, neural networks are the state of the art for, you know, most major natural language processing tasks. And it's crazy because, you know, this is a huge change from, like, let's say 2012 until now. It used to be that linguists thought about how to do natural language processing. And now neural networks use very little linguistics, and it's basically just a big computational engine. So, okay, so that's one big use case, which is really interesting. Another big use case is computer vision. So I already kind of alluded to this, but again, this is very impactful. So problems in computer vision, and I'll do some examples of this actually in a bit. So you can think of the XK as being an image. You take with your camera, okay, let me be a little bit more specific. So what is an image, in fact? Well, an image, you can think of it like this. An image has 3 color channels, right? It has red, green, blue. Red, green, blue, that's the typical color channels. And then it has some number of pixels. You know, if you have a 100 by 100 pixel image, it's going to have 100 squared pixels, which you can think of as the spatial dimensions, n by n here, of the image. So actually, to a computer, an image is a order 3 tensor. It has 2 spatial dimensions, the x and the y coordinates, roughly speaking, and then 3 channel dimensions, red, green, blue. So that's what a computer sees. And then, you know, the typical output might be, again, I'll do a binary classification type output, you know, 1 or 0, depending on whether XK has a human or not. That's another kind of good example. You know, again, we are very good, given an image, to see the humans. Okay, the human could be wearing camouflage, we might not be perfect, and so on. But for a computer, when the image is just a collection of n squared times 3 scalars, it's not so easy to figure out if there's a human in the image. But okay, the applications of this are widespread. So first of all, self-driving cars, at least, I don't know about first of all, but that one captures my imagination at least. You know, the basic problem is you have some sensors, they sense the world, and the world looks like images. That's the point. And you need to somehow process them to extract information in real time. And, you know, I'm not an expert in self-driving cars, but as far as I know, under the hood, the main workhorse is specific kinds of neural networks called convolutional neural networks, which I'll briefly describe later. Okay, so that's one application. So there's facial recognition as well. That's a kind of really interesting use case. You know, that one has ethical difficulties with it, but it can also be very useful. Okay, so hate it or love it, that's this use case. Okay, and then the last use case, which is actually how I got into neural networks, what seems like a million years ago now is what people call reinforcement learning. So in reinforcement learning, this one maybe is the least familiar to people. You can think of it like this. The input is the state of some system. So you can think roughly something like the position of a chessboard. Okay, so there's some usually enormous possible number of states for a system, and xk might be the current state of that system. And then your goal, f of xk, might be to find the reward maximizing action. Okay, so there's some space of actions like the next move in chess, and you would like to find the best one. In other words, the best next move. Okay, so you would like to have some evaluation procedure which says, okay, moving your queen to d7 is, the best move because, it's the one that gives you the highest probability of winning. So, of course, chess is played by computers using neural networks these days, and chess engines are way better than humans are. A lot better. I got into it because of AlphaGo. This was a computerized system that used neural networks to play Go. This is useful also in any kind of task, which can be recast in reinforcement learning, which is like almost anything. So for example, you can think about like exploration by like an autonomous vehicle. You want to like find resources in some environment, and the current state of the environment is, the map of what you've explored, comma, your position, and you would like to know where should I go next. Okay, so to get as many resources as I can, or to minimize the power expended to get to some point I want to get to, or whatever. Okay, so those in my mind are the three main use cases, and at the very end, I will come back and I will say something about the challenging things that are still on the horizon, areas where neural networks are just starting to be used or haven't been used successfully to a large extent, but probably could be. Okay, so I wanted to say that, and now I want to dive into neural network optimization. So I want to tell you, if you're actually going to use a neural network, what kind of things should you be thinking about? So to be fair, I certainly cannot do justice to this topic, in part because, I'm somebody who mainly does theory, and so it's not as if I optimize neural networks all the time. But okay, my colleagues at Google this semester do a lot of neural network optimization, and the bottom line is that it's complicated, and it's finicky, and you have to set things just right, and so there is no golden rule for things. But okay, nonetheless, so let's just remind ourselves what a neural network was. Right, so here we have a vector, two-dimensional vector of inputs x1, x2. And I'll again draw a layered network with two hidden layers, and then maybe an output, maybe a two-dimensional output for fun. So maybe my wiring diagram looks something like this. Oops, that was a bad wire, but I think you know what I mean. So these are my outputs. And then, so this is n of x theta. So it's quite useful actually to add one more fictitious node, which I'll draw maybe in red here, and just think of this as being the loss function that you're going to be minimizing on your data set. So you think of there as being two extra wires. And the reason that it's okay to draw this is that the loss function depends only on the outputs of the network typically. Okay, so it really is this compositional thing where you start with the input x, you go to the first layer, you go to the second layer, you go to the output, and then based on the outputs, you ask how well did I do on my data set. So this is a legitimate thing. Okay, so what I told you, and I want to spend some time now discussing this in more detail, is that neural network optimization is done by some variant of gradient descent. So I call it Sgd. Okay, so suppose you have some trainable parameter somewhere in the network, and this is, let's say, this weight, which connects, the first component of the input to the first neuron in the first layer, some weight W. So gradient descent, we teach our students in calculus, looks like this. The update to W is minus a learning rate lambda times the derivative of the loss function with respect to W, right? You go in the negative gradient direction. And this scalar here is what people call the learning rate or the step size. Usually in the neural network world, they call it the learning rate. Okay, so fine, this is how we do it. And then how do we actually go about doing this computation? How do we numerically compute this DLDW? Well, this is kind of a beautiful idea that goes back to the 70s in various contexts. Okay, so we actually numerically compute the derivative of the loss with respect to the weights using an algorithm called backpropagation. Backpropagation. It's a very 70s and 80s kind of name, so it fits the genre. But backpropagation is just a fancy way of saying chain rule. Okay, I'm not going to try to write out the mathematical formulas, but to compute the derivative of the loss with respect to this weight here, we basically compute the derivative of the loss with respect to the outputs of the network, then the derivative outputs of the network with respect to this last hidden layer, and we recursively peel back the layers of the network until we get back to the weight W. Okay. So I won't say anything else about that, but all I'm saying is that there's some numerically efficient way of computing all of these derivatives called backprop. Okay, so now there's going to be a couple of wrinkles, and I want to talk about several aspects of how we actually do gradient descent. One aspect will be how we choose the learning rate. One aspect will be that, in fact, instead of actual gradient descent, we do what's called stochastic gradient descent. So I need to say something about that now. So let me start with SGD. So S stands for stochastic. And stochastic gradient descent is a slight twist on usual gradient descent, and it goes as follows. So let's just remember somewhere. I will write it here. Sorry, let me erase this loss here. And let me just remind you what the loss looked like. So remember that the loss on a data set looked like the average over the data set, or the sum over your data set, the average over the data set of the loss on each data point. That's how we wrote it. So this will be important right now. So here's how SGD works. You start by, to make a step, randomly selecting a batch, as it's called, which is just a subset script B of the data set. Okay, so B could have one data point in it, or it could have 100 data points. It depends, and we'll talk about that. And then rather than actually computing the full loss, you replace the loss over your data set by the batch loss. Okay, I'll write an L sub B, and this is nothing more than the average over your batch, the sum over elements of your batch, the loss on each element. Okay, so here, the whole point of stochastic is that this is statistically going to be similar to the full loss, L on the data set. And the reason is that if you uniformly at random select a batch and you average over the batches, then of course the average over the batches is nothing more than the actual loss that you started with. So this parameter here is very important, and it's called batch size. It's just the absolute value of B. That's my notation for the number of elements in your batch. So the intuition is just like this, that this is a good thing to do. So this is good. At least this is the reason it was originally introduced, because small batches mean less computation. Okay, the point is that if you fix a batch size, you only have to compute the gradient of this per sample loss on as many elements as you had in your batch. So if you have a small batch, you can try to save some computation. But okay, as I'll explain now, there are some issues with doing this. Okay, and the key question that I want to address, although it might not be completely obvious that this is a sensible question to ask at all, the key question is how to choose the learning rate and the batch size. Okay, in practice, the fact of the matter is that if you incorrectly choose the learning rate and batch size, your network will do extremely poorly. And so I want to discuss why that is intuitively and say at least a little bit about what kind of the state of the art is for actually making this particular choice in optimization. Okay, maybe before I do this, let me stop briefly and just ask if the setup is clear. because if I didn't do a good job of explaining gradient descent, then nothing I say, of course, will make sense. So let me take a question or two if there are any, and otherwise I will just continue on. Questions? It's clear. Okay, looks like it's clear. So let me try to build up our intuition about how to think about the batch size and the learning rate. These are two constants you have to set in practice. Intuitions. And they're kind of fascinating, at least to me. All right, so here's the first intuition. Intuition number one is that let's think first about the learning rate. So small learning rate corresponds to slow but accurate optimization, whereas large learning rate corresponds to fast but noisy optimization. Okay, so why should this be? Well, okay, let's draw a simple picture. So let's illustrate this like this. Imagine that this is the function L that I'm trying to optimize, and in my cartoon, I just have one scalar variable theta. So let's imagine that we start over here. This is our current setting, theta naught, for the start of optimization. Well, suppose first that we have a small learning rate lambda. It's going to be slow because the step sizes will be small, but it'll be accurate because, you know, the gradient tells me what direction locally to go to minimize the function. So if I have a small learning rate lambda, I will eventually converge to theta star, which is indeed, in this case, the global optimum. And I'm very happy that I was able to find the global optimum. But, okay, maybe it was slow and I want to start taking bigger and bigger steps. So what happens now if I take a slightly bigger step? Well, if the step size is smaller than the width of this valley, then I will converge to theta star, but I may not converge monotonically. I might go to this side, I might overshoot a couple of times. Okay, and that's the first inkling of what it might mean for larger lambda to be fast but noisy. You take big steps, you in general try to get to the minimum faster, but you might not be literally decreasing the value of the function every time. It's sort of more complicated. And then the worst case scenario, if lambda is too large, is what if our first step actually just takes us to another basin? What if this is theta 1? Well, then you might imagine that you just forever stay here. You bounce around in this basin, and you might eventually learn theta star here. And that's unfortunate because now the optimum that you found is actually not a global optimum. It's only a local optimum. And so maybe you haven't done a good job of fitting your data or whatever else. Okay, so I'm sorry to give you a crash course on optimization in 1 second, but this is the kind of picture that at least I have in mind for what small and large lambda is supposed to tell me. Okay, I'm going to delete this picture now so that I can keep writing intuitions. No, that's bad form, but I'm going to do it anyway. Okay, so amazingly, you might tell yourself, well, why would I choose the same lambda for all parameters? Right? In principle, in this update equation, where just in the definition of gradient descent, I could make this lambda depend on the parameter that I'm updating. Right? This isn't such a crazy idea because the output n of x theta might be very sensitive to one parameter, let's say to theta 1, but not to another parameter, theta 2. And so if you have different sensitivity to different parameters, why are you taking equal steps in those directions? Okay, so indeed, in practice, you don't always choose the same learning rate for every parameter. There's a bunch of words associated to this, things like attograd or atom, RMS prop. There are various things people do in practice one way or the other to set the learning rates differentially. And I'm just saying that if you're actually going to use a neural network, you might consider doing that. Okay, but let me just give a cartoon illustration of why you might care. So imagine that the loss function L d of theta roughly looks like this. It's just epsilon theta 1 squared plus theta 2 squared. Okay, there's just two parameters, theta 1 and theta 2, and I've taken a small constant in front of one of the terms. So this is a very simple loss. It's convex, and in fact, its level sets are just elongated ellipses. Right, the optimum is here. Here's theta star equals 0. That's, of course, the global minimum of the loss. But the kind of problem that you run into is that suppose you're at this point. This is where you are. That's theta 0 or theta current. So the direction you would like to go is, of course, the direction that points you towards the global minimum. But the direction you actually go in gradient descent is the direction that's orthogonal to the level set, right? That's the ellipse that I drew. And so the issue is going to be that when you have this kind of very different sensitivity, you are going to eventually make it to the minimum, but you'll kind of have this very, let me draw it in a different color. You'll have this very zigzag kind of trajectory. You'll keep overshooting, and it'll be very inefficient. So this is kind of a cartoon for why you might want a different optimization scheme where you don't set the value of lambda to be the same constant for all parameters. But okay, so what's the downside to doing this? The downside is actually kind of brutal, okay? And so this is the sad state of the art. So in practice, how do you set lambda? Well, you set lambda as follows. You find lambda literally by grid search. By grid search on log space. So what does this mean? Okay, I will, I guess, erase this picture so that I can show you what it means here. Yeah, I'll save some room. In fact, let me just move this up so that it looks a little nicer. Okay, so what this means is you might say, okay, a priori, I think lambda is going to be between 10 to the negative 6th and 10 to the 0. And I will just have, you know, equally spaced points in log space. Okay, I didn't do a great job of making them equally spaced, but you know what I mean. And then you literally take a uniform grid of points here. You do a little bit of training for every one of these choices of lambda. And you ask which one starts to train the best. And maybe the ones in this interval train the best. So then maybe you'll expand this interval out, again in the log scale. And again, you'll take a grid here. And again, you'll do a little bit of training, and maybe you'll find this was the best learning rate, and that's the learning rate you're going to stick with. Okay, if this sounds like science fiction, it's a little embarrassing, but it's really what people do in practice. And now you see the problem of having different learning rates for different parameters. You have to do this grid search for every learning rate, right? So if you have a billion parameters and they each have their own learning rate, you're going to be doing grid search in a billion dimensions, which is obviously impractical. Okay, so that's a disaster, but that's how people do it. And without doing this, your model will not actually work well. So let me delete this. That's what I mean by grid search. All right, here's another question. Okay, if you are into optimization theory, this is a natural one. Why keep lambda constant during training? In the end, you know, that's not very reasonable. As you get closer and closer to the minimum, maybe you want to be more and more conservative and take smaller and smaller steps. So indeed, this is what people call learning rate schedules. And there's a bunch of schedules. You know, there's the constant schedule that's popular in practice. There's the decaying schedule, so lambda decays, which just means lambda gets replaced by, let's say, 0.9 times lambda every fixed number of steps. There are more exotic ones. Lambda is periodic is a common one that people use, and it's really kind of good in some situations. You know, lambda of t is like the absolute value of cosine of 2 pi kt or something like this. So, you know, it's crazy that this is something people would even consider, but these kind of schedules that people use, I'll call them schedules, it's incredibly important to know that there are different schedules available, because again, sometimes constant learning rate just will not do well, and you need to do cosine scheduling, or you have to do something even fancier. There's lots of fancy variances. So you should be aware that this is a thing people do. Okay, so that's sort of what I want to say about the learning rate lambda. And what I'd like to now point out is that actually the batch size B and the learning rate lambda are not such different creatures. Okay, so this is intuition number 5. So you notice that I phrased the question, how to choose lambda and B. And you might have been asking, why do you choose them jointly? Well, that's actually because they're kind of related parameters, and you cannot separately optimize them, it turns out. So the simplest way I know to see this is, imagine trying to ask, what's the effect of taking small batch size or the effect of taking large batch size? Well, okay, so the effect of batch size is over here on the left. It's in the kind of random estimate you have for the true loss L that you're trying to minimize. So if you have a small batch size, what happens? Well, it means that you're replacing a big average, which was LD, by an average over a small random subset. So this means that you're going to have noisy but fast optimization. Fast because you only have to compute the gradients on a small subset. You only have to differentiate this per sample loss. Okay, and similarly for large batch size, you're going to have accurate but slow optimization. Okay, so if you haven't yet dozed off, you will notice that these words were exactly the words that came up for small and large learning rate. And so in fact, the point I want to make here is that lambda and batch size are inversely related. Increasing, oops, I didn't spell related correctly. There we go. Increasing batch size has the same effect, at least to a large extent, as decreasing the learning rate. And so in practice, what people will often do, and I'll write this in red, is they will often think about the product of them as being held constant. There's some theoretical reasons to believe that the product is the right number to keep constant. There are some theoretical reasons to believe that it's the wrong number to keep constant. Some theoretical arguments show that it should be batch size to the 1/2 power. Empirically, it's not completely clear what the right answer is, but this is sort of the state of our understanding. We don't fully know how to choose the batch size, and so we just do something reasonable and hope. That's pretty much how it works. Okay, so that's the end of what I wanted to say about choosing batch size and learning rate. I wanted to go on to architecture selection after this. But again, let me briefly pause for some questions, and then I'll proceed on to architecture selection.
Hi, Boris, I have a question. When you said a small learning rate can be accurate but slow,
yeah,
it makes it sound like it's good, but you might get stuck in a local minimum if you choose a very small learning rate, right?
Yeah, you're totally right. So there are questions about local versus global optimality, but imagine, like, I think a good situation is that what I mean by accurate is just that you have a good estimate of the true gradient. The gradient of the loss function L only locally certifies the direction in which you need to go to decrease the value of the function. And so choosing lambda to be small means you're at least accurate in locally minimizing the function. And you're totally right, you might not be globally minimizing. But it's slow because you take a small step. So that's one sense in which you can have accuracy. And if you kind of want to take the extreme version of that, imagine that your global minimum is just in a very narrow valley. If your learning rate is too big, you will never stay in that valley because it will, just the random fluctuations in, for example, how you choose your batch will kick you out of that valley of the global minimum. And so that's kind of another way of thinking about the accuracy. I hope that's kind of helpful.
Thanks.
Yeah. Other questions? No one is brave enough. And maybe it's all just so clear. That's unlikely, I think.
I have a question first. So you said for this stochastic gradient descent, we randomly select the batches, right? Every time that we're picking a batch. So we're not learning anything during doing this over these iterations. So why do we keep doing it just uniformly at random?
Oh, no, I mean, we are learning a lot. The batches are part of the data set, you know.
Sure, I mean, why do we keep choosing them at random, totally at random?
Okay, so there's two reasons. One reason is obvious, and that reason is you want to save computation. You know, if I have a small batch, I save computation. That's great. I choose it at random to make sure that all my data points actually have an influence on the function I learn. Right? I don't want to sacrifice the fact that I have a potentially large data set. A less obvious reason is that having a small batch introduces noise because you don't actually use the full gradient of the loss. You're using a random estimate for the gradient of the loss. Now that might seem like bad, but actually empirically, it's really good to have that noise. For reasons that are somewhat contentious, let's say, and I will say not well understood.
I see.
So that's the kind of two considerations. Yeah, it's a little strange, but it's true. It's true, and you know, I think it'd be nice to have more of a theory for it in some sense.
Thank you.
Of course. Okay, let me go on so that I can say something reasonable about architecture selection, and then again I'll take more questions afterwards if people have questions. All right, so here we are, you know, we now know everything about neural networks. We know how they work. We know how to choose lambda and the batch size, except we haven't actually answered the question of how do you choose the wiring diagram? I mean, if you don't know how to do that, then who cares if you know how to do the batch size and the learning rate? Okay, well, that's a good point. And, you know, I have good news and I have bad news. Let me start with the bad news. The bad news is that the best architecture is always data set dependent, is always data dependent. Okay, what do I mean by that? The good news is that I don't mean it in such a serious way. Okay, what I mean is that if you're generally doing a natural language processing problem, then we found that there are maybe two good kinds of architectures. And I'll just say the words, but I won't really say what they are. So there are transformer-based architectures. These are use what people call self-attention. And then there are recurrent architectures, which are things like what are called long short-term memory, and attention and possibly self-attention, and okay, lots of bells and whistles, which are beautiful, but I don't really have time to get into. So I'm saying if you have a general domain like NLP, these days, although people would be interested if you found a better architecture, we've kind of converged on two kinds of general architectures, which are something systematic about the wiring diagram. Okay, in computer vision, in contrast, the architecture is rather different, and you know, the state of the art for almost all computer vision problems is, at least at the heart of the matter, is what's called convolutional residual. Okay, so it's both convolutional and residual, and that's the best we do. And this one is a little bit more principled, and I hope to be able to say something about it in just a couple of minutes. That's sort of what I'll end on. Okay, but what I want to say is that although this is, of course, a very nice guideline to have, it leaves many choices to the practitioner. So it still leaves many choices. What kind of choices does it leave? Well, let me give you some examples. So first of all, the details of the wiring diagram. So, you know, I might tell you, in general, you should have layers that, you know, do something of the form of computer convolution. I'll draw what that is later. But then you might ask, how many layers? You know, how wide are the layers? Exactly what nonlinear function should you use, and so on. So this involves things like width, depth, ... Okay, so then there's always the question of the choice of the nonlinearity sigma. And usually, at least let's say for computer vision, the ReLU is just, you know, the winner at the moment. Remember, that's just the maximum of 0 in the input. But no one said that tomorrow someone won't invent a better activation function. And then, quite importantly, it leaves open to you how to initialize the network, that is, how to start training, and how to optimize. That is, how to choose things like the batch size and the learning rate and so on. Okay, so we talked a little bit about how to choose those, but still you have to actually numerically implement that and do some kind of grid search or do something sensible. Okay, so my purpose now is I want to give 2 brief intuitions about how to do some part of architecture selection. And both of these intuitions have to do with trying to understand the role that depth plays. I said at some point that deeper networks tend to do better in practice. And so I want to say something about that. Okay, so one empirical observation, I already said this before, but it's important, I'll say it again. Deep is good with an asterisk. Remember, the asterisk was meant to say, so if I had a footnote down here, asterisk means but often less stable. So it can be more finicky to actually optimize. And I want to explain this asterisk at least a bit, because it puts into context what a residual network is. Residual connections are basically invented to make neural networks more numerically stable. So let me try to draw this picture. So here, again, I'm going to have some kind of neural network. By now, hopefully this picture makes sense. And I have my favorite wiring diagram. I don't know what it is. Maybe this is my wiring diagram. So again, I'm going to think of this as being the loss. This node here. Oops, I need to have a normal pen. So this is my loss. This is the output of the network. These are the inputs, x1 and x2. And maybe I have some trainable parameter, w, this weight here. Okay, so I need to compute, remember, the derivative of the loss with respect to the weight w. That's the fundamental object in doing gradient descent. So how am I going to do this? Sorry, I can't help myself. I need to put this dot in the proper place. Okay, good. So you're going to do it by the chain rule. You're going to say that, look, W only affects the loss through the values of the output. So that's the first chain rule application. This is DL, DN. And then N depends on W only through the values at the second layer. So maybe let me give them some names. So this is the value computed at this layer will be N1, the value at this layer will be N2, and then N3 is the output N. So it only depends on what you computed after 2 layers. And dn2, dn1, and then finally dn1, dw. Okay, all I'm saying is you can use the chain rule when you have a layered network. And now you see the following problem, right? So in general, this intermediate term here will be a product of approximately number of layers Jacobians, right? Each of these terms is the Jacobian, for example, this term. This is the Jacobian of what the network computes after 2 layers with respect to what it computed after 1 layer. So, and this is a product of many, many Jacobians if you had a deep network. Here I only had depth 2, so I had 2 Jacobians. And these kind of matrix products are often very numerically unstable. Okay, so if D is much bigger than 1, then these kind of products, and therefore the whole derivative, dl dw, will often be kind of poorly conditioned. So it means it's either going to be very small, or it's going to be very large, which I'll write this way. And this even has a more or less fancy name called the exploding and vanishing gradient problem. Vanishing gradients. Okay, so this is a basic intuition about deep neural networks, which goes back really to the early 90s, to the work of people like Jürgen Schmidt-Huber. And they noticed that if you have to compute many of these Jacobians, you might be really worried that the product either squashes everything to 0 or blows everything up exponentially in the number of terms. And both of these numerical instabilities just mean that optimization cannot possibly work. right? If your gradient has size 0, you haven't done anything. If your gradient is huge, let's say bigger than machine precision, then you've just re-randomized that parameter and set it to an absolutely arbitrary number. And so no optimization is possible. Okay, so one of the ideas that people had for how to overcome this is to introduce residual connections. So let me draw this on the next slide so that I can have plenty of room. So this is the first kind of architectural choice that you might want to consider making, is to use a residual network. It has its own downsides, but I won't get into it too much. So let me heuristically introduce what a residual network is. So it looks like this. Here's my input X. I will no longer draw the individual neurons because it gets to be a mess. And N1 is my first neural network. So you might process X by putting it into N1. But you might also decide to skip the computation done by N1. And this plus here is just an addition. And then you keep going. So you might choose to process it using the network N2, or you might skip it. And so on, and eventually you get to the output ND. Let's say if the depth is D, and that's the output of the neural network. Okay, so the formula is just the following, that the output is equal to, well, okay, you have X, that's what happens if you skip all the networks. And then you have the first order correction to X, which is computed by going through N1 and then skipping all the networks. And then you have the second order correction to this first order correction, which is N2 applied to the first order correction. Okay, plus dot, dot, dot. That's what residual networks look like. And the basic intuition is very simple, that N sub j is the jth order correction to the trivial map, to the map X just as the identity. So in other words, you say, rather than learning an arbitrary function, I'm really going to learn a perturbation of the identity, which does interesting things. And this is going to make my computation more stable. Okay, so that's the basic intuition. Indeed, in practice, residual networks had a huge effect when they were originally introduced. And they're completely standard for computer vision problems in particular. And so they typically are state of the art there. And like I said, the intuition is that rather than computing just one fixed nonlinear function, you're going to iteratively compute corrections to a simple function like the identity. That's how residual networks work. Okay, so that should definitely be in your tool bag if you're going to use neural networks for something. And the second thing I want to say is what a convolutional network is. So convolutional networks are beautiful things, and I want to try to explain them at least very briefly. Okay, so this is my second kind of explanation of how to deal with deep networks. And this is specific to computer vision problems. Okay, so I already kind of said this, but I want to draw the picture again. So in computer vision, the inputs are n by n, where n is the number of pixels, RGB tensors, right? So the picture looks something like this. And I'll draw that picture. So it's a three-dimensional array of numbers. And it's important that it's three-dimensional because the dimensions have different meanings, right? Here's the red, green, blue, and these are the channels, as they're called. And then you have the pixels, which fill out the physical space. So you can think of this as X and Y coordinates, which describe space. And then there's another set of coordinates which don't mean anything in space, but there's some kind of other features called channels. Okay, so the point of a convnet is the following. So in a convnet, and I'll draw a picture in just a second, convnet obviously means convolutional network, every layer has the same structure. Layer has this kind of channels by XY coordinates structure. Okay, so that's how they work. That's point one. And then every neuron in a layer shares weights. Okay, so now let me draw the picture. right? So the key, maybe I will write it here so that we can see it next to the inputs, is you want to say, look, I want a structure of a neural network that respects the fact that I know that my input is an image of the natural world, right? Pictures you take of the real world are highly structured objects. And you want to understand how to use that in creating a neural network to efficiently process them. So the key is the following, that images in the real world are hierarchical and local. Those are the two properties I want to talk about. So what does it mean? Local means that nearby pixels are highly correlated. Hierarchical means that the high-level features of the image, for example, if you have a cat, are built up hierarchically over small features. You know, you might look in different patches of the image and say, okay, oh, I see some fur here, and I see some whiskers here, and I see a tail here, and I see some paws here. And I put those things together and I make a cat. Okay, roughly speaking, that's the kind of idea. So let me try to draw, okay, to the best of my limited drawing skill ability, what a convolutional layer looks like. So let's imagine that, just so that I don't have to keep drawing three-dimensional images, I have a one-dimensional image. Okay, I still have three channels. I'm drawing the red, green, blue color channels of my image, but now I just have an X direction. So this is red, green, blue, and this direction is the X direction of the image. And now I'm going to make another layer, which has the same structure, but which may now have more channels. So maybe it has, rather than 3 channels, it might have 4 channels. And channels are just an abstraction. They don't really mean much. They're just some kind of correlated features. So the whole point is now the following. Here's the wiring diagram. So you take a neuron in this first channel that I'm drawing in blue, and every neuron will look the same. So for instance, this neuron is going to be connected to all of the pixels at the same spatial location and throughout the color channels. Okay, and every neuron in this layer, in this first layer that I've drawn as blue, will have the exact same weights. So the wiring diagram is that things are locally connected. You know, this represents a localized area of space, and this represents a localized area of space. They're both X coordinates. And the wiring of these blue wires I have here, if I were to draw the same wires for this neuron, would literally be the same. And this means that every neuron in this first channel is looking for the same pattern, but in a different part of the data set. Okay, so let me say that somewhere. Yeah, so I'll just write it here in blue. So all neurons that are in this blue color channel look for the same pattern, but at different spatial locations. Okay, so, but if I go to the red channel, for example, maybe that's what I call the second channel, then, okay, again, the wiring diagram is local in the sense that this neuron is connected to all the spatial locations and the channels of the previous layer. So maybe like this. I don't think I missed any. But these red wires are going to have different values than the blue wires. And what that means is that your network is going to be searching for a different kind of structure, a different feature. You know, blue might be fur, red might be whiskers, roughly speaking. And you stack many, 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 many of these layers on top of each other. And each layer extracts hierarchical features from the previous layer. Maybe the first layer extracts edges, and then the second layer extracts confluences of edges, i.e. corners. And then the third layer extracts, you know, from corners, it extracts shapes and so on. Okay, that's some kind of cartoon of what's going on. Okay, so I don't have much more time. Maybe just I will take 1 or 2 more minutes to finish up, and then I will take questions, and I'm happy to discuss. So that's the second answer to how to kind of do architecture selection is, at least for computer vision problems, you should use convolutional networks. They're sort of biologically inspired. They're not so different from how our brain actually works, although, you know, it's not a perfect match. Okay, so let me just finish by outlining what I think of as some of the challenges of deep learning, you know, and things going forward. So one challenge that I think is really fascinating is to find new use cases. you probably got the sense from this last part of the talk that both for natural language processing and then for computer vision, people had to do a lot of tweaking about the kind of architectures you use to solve the problems. And so, there are many things we would like to be able to model. For example, doing PDE modeling, of, let's say, fluids, like climate modeling or modeling of arterial flow or something like that. Maybe we want to model physical systems. Maybe we want to do chemical simulations. Okay, you want to find the ground state of some atom, or you want to learn how to make a new good inorganic catalyst or something else. Okay, so this is difficult because we're often not completely sure what kind of architecture to use and how to set it up and whether the problem is tractable and so on. People are certainly starting to do it in this case though. So another one that strikes me is biological data. I'm thinking specifically here of genomics data. Gene expression data is this incredible repository of massive data sets that we just don't know how to process extremely efficiently, unfortunately. We still don't understand a lot. And there have been many attempts to do biology and specifically genomics using neural networks. And from my point of view, they've been rather unsuccessful. Okay, so challenge number 2, aside from different directions, is, let me just mention actually only this challenge. I had a bunch of them listed, but I will refrain. But this one's extremely important. So this is something called distribution shift. So the idea of distribution shift is that the nature of your data is always going to be changing. That might sound silly. I mean, a stop sign is a stop sign is a stop sign, except that's not true, right? So here are some examples. So first of all, you might have change in hardware. Your job maybe is to do medical diagnosis with neural networks. That's great. And you have a beautiful MRI machine and you've trained your neural network, given an MRI scan to figure out, how to do a diagnosis. Fine, but now you bought a new MRI machine and, if the outputs are not literally the same, it's not quite calibrated in the same way, maybe it has better resolution, maybe it has more features in it. How do you make your neural network resistant to distribution shift in this sense? That's one example. Another example is maybe sunny versus cloudy. That's how I think about it for self-driving cars. Believe it or not, this is a big problem. If you train a self-driving car to drive in sunny weather, and then you ask it to drive in cloudy weather, it's going to do very poorly. For us as humans, we don't really even register the difference. Our eye is a beautiful thing. But for computers, it's not so obvious that change in the overall intensity, even just a constant contrast change is not important. So this is kind of a big problem. And what underlies both of these things, and this is what I'll sort of end on, is that neural networks tend to be brittle. And what I mean is best illustrated just by a kind of silly example. People do this all the time. So you take a neural network that has been trained on a self-driving car. And what you do is you take a stop sign and it is 99% certain that it's a stop sign. Let's say 99.9%. It does a very good job of detecting the stop sign. Then you put somewhere here a post-it note, small yellow post-it note. And now the 99% goes to 99.9% fire hydrant in the computer's mind. Oh, I don't think I spelled that right. In the computer's mind. And of course, that's a total disaster. And so this silly example, first of all, is true. People did this kind of experiment and is just universal. You take any neural network and you slightly change the nature of the input by some kind of relatively small perturbation. And very often the neural network will just completely break. And so solving this issue is important, both theoretically and practically. And I think about, how to model these questions and how to kind of get some insight into them. That's one of the things I'm very excited about these days. Okay, so that's the end. That's all I wanted to present. I apologize for running just a couple minutes over what I said, but I'm still under the time limit. So let me take some questions and I'm happy to have a short discussion.
Hey, Boris, you gave a terrific workshop. Thank you. You mentioned the challenges What do you think are some of the promising areas of research that could solve some of those challenges, or at least moving towards the direction of addressing those challenges?
Well, yeah, okay, I outlined two very different challenges. So for the new use cases, the point is, I think whatever big use case you want to tackle, you have to think hard about how to adapt the neural network to that setting. How do you bake into the wiring diagram and the way you set up the optimization and the way you represent your data in a vectorized form, the kind of most important essential knowledge about the nature of the use case that you're doing. In a physics model, that might be something about conserved quantities. In, some kind of setting of NLP, it might be that, words aren't just random vectors, there are semantic relationships between words. There are also syntactic relationships between words or phrases and so on. So that's the kind of research that I don't have much insight into, in the sense that I generally think about theory. And if you asked me, what does it mean to be, a sentence? That's kind of a deep question. And I'm not sort of well designed to answer it. But I think that's one promising thing people are doing. For simulations that are PDE based and for genomics data, people are thinking hard about, for my kind of problem, what's the right framework to represent my data and the right kinds of wiring diagrams that will encourage the neural networks to do a computation which is somehow reasonably kind of aligned with the nature of the data. Okay, on the other side, on the distribution shift, people are working really hard to understand why neural networks are so brittle and, therefore how to overcome that. And I would say the jury is still out. There's a lot of really interesting work, both on distribution shift and on adversarial examples, which I slightly conflated, but I didn't want to distinguish too much, and I don't know what to say about it other than, I've probably heard on the order of 100 talks on that subject. And they're interesting, but there's no consensus about what's going on. There's lots of theories.
Okay, may I ask a question? Do you hear me?
Yeah.
Okay, my name is Vadim Anshelovich. First of all, thank you very much for your excellent presentation. And my question has two parts. First, are there any problems for which is known that neural network approach you describe doesn't work? Or using different terminology, are known counterexamples which shows that neural network approach is not universal? If yes, can you give us one or two examples?
Yeah, so that's a very good question. That's, of course, closer to my area of expertise in a sense, because I'm sort of more of a theory person. So let me put it this way. What does one mean by an example? It really depends who you ask. People who do computer vision would say, oh, look, computer vision is an example of where neural networks work well. And you say, yeah, but what do you mean by, what does it mean that your training set comes from a computer vision problem? What are the statistical assumptions on the data? And what are the kind of, what's the statement that with high probability over some randomness, some optimization will not only kind of get the global minimum of the loss, but will also have a certain generalization error, some kind of statement like that. So what I would say is that on that kind of more theoretical side, the main thing people know is that in the limit of neural networks where they're very wide. So if you remember, the width was the dimension of the hidden layers. So if you take a neural network, so maybe I'll scroll up to where I had the, so maybe I'll go to the very beginning over here. All right. So you take a neural network, let's say it looks like this, but instead of the second layer having dimension 3 and the first layer having dimension 3, you say they have dimension n, and you let n tend to infinity. So then there are a number of theorems which guarantee at least the success of optimization, which say that with high probability, you will in fact drive your training loss to 0. That's statement number 1. But then those theorems really proceed by showing that in that limit, at least, under some other assumptions on their learning rate and all of this, your optimization procedure reduces to a kernel method by a kernel that's actually determined by the architecture of your neural network. So the parameters that remain are the nonlinear function you have, and the number of layers, because we've already sent the layer widths to infinity. And so once you can prove that the kernel is non-degenerate, then okay, of course, kernel method is going to work. And so there are theorems also of that nature. And those theorems are very, very generic in the sense that, you know, as long as you have samples from an IID distribution that, let's say, has full support or something like this, or, you know, has like top dimensional support, then you will be able to fit the data and also generalize at least as well as, you know, kernel methods will generalize with this kind of kernel. There's some guarantees like that. There's also another strand of research which relates the optimization of wide neural networks to interacting particle systems, and in particular to optimal transport. So optimal transport is kind of a classic problem about how to optimally match two distributions. And it turns out that gradient descent for infinitely wide networks with one hidden layer exactly corresponds to optimal transport, at least if you're doing mean squared regression. And so then you get another set of results which say, okay, since they correspond to optimal transport, we know a lot about optimal transport. You can plug in what you know and say you're guaranteed to succeed with this complexity on the number of steps. And, you know, with this error, you can do kind of pack learning, roughly speaking. So there are a number of results in those directions, but the results are kind of incomplete. There is very little understanding of what happens for actual practical neural networks that are not infinitely wide. And, you know, there are theorems which now say that stochastic gradient descent with wide enough neural networks is a universal optimization scheme. But then, as you say, there are examples. If you have, like, you know, a width 5 neural network, you could easily have lots of bad local minima, and you're never going to optimize. In fact, with high probability, you will fail to optimize, this kind of thing. So the literature is kind of convoluted. I don't think there's a very clear story. But if you're interested, again, you should send me an email, and I will send you the references where hopefully in the email you can just detail the kind of thing you would like to see, and I can send you links to the papers I know exist.
Okay, thank you very much. Let me maybe specify my question a little more. Do you know any examples of problems, or maybe say hierarchy of problems, which depends on large parameter, that you can get good enough interpolation, I'm using your term, but you cannot get, in principle, good enough extrapolation or generalization? Do you know such examples? Or do they exist, or there is some reason for them not to be in existence?
So okay, I understand your question, and what I can say about your question is the following. There are two important parameters, roughly speaking. One is number of parameters in your network, or some other complexity measure like this, but let's just say number of parameters. That's one large parameter that I'm talking about. The other is number of data points that you have. And so in the regime where the number of parameters that you have in your network is much larger than the number of data points, then you can say a lot about optimization. And you can say some things about generalization, but less, unfortunately. And that's because this kind of over-parameterized optimization and generalization is hard. You know, if you think about, like, for example, using Rademacher complexity or VC dimension to give generalization guarantees, they're completely vacuous in the case where you in principle have more parameters than data points. And so that's not great. And people are still trying to work out a theory. You know, there's a lot of papers about a really beautiful subject called double descent, which says that, you know, as the number of parameters grows, first your test error will go down, then it will go up, and then it'll go down again, which is the weird thing. And so there are linear models and kernel methods in which you can prove that such a thing happens. But for neural networks specifically, I don't know a single example that has been worked out that shows this kind of generalization guarantee. I just don't know how to do it. Okay. It might be out there, but I just don't know.
Thank you very much.
So Boris, at one point, when you explained the choice of the architecture, you said that there are still many choices, to be made, right? You mentioned the variant, the sigma function, the optimization. You didn't really specifically mention the loss function. Is the loss function right now pretty much universally chooses a square loss, or is that something being debated? Is that square loss is the best loss function to use? Is something else can be?
That's a good question. I should have mentioned the loss. So, okay. The main thing to say is the squared loss is definitely not a good loss. I just use that as an example because it's easy to state. It's usually not used, in fact. So for classification problems, where your goal is to basically output a probability distribution over a discrete set of labels, the loss that's almost always used is just the cross entropy loss between the current distribution you're outputting and the delta function on the correct answer. Okay, so that's pretty well established and seems to work well, but that no one says that that's optimal. That's just, practically speaking, what people do. For more complicated problems, the losses, I think, vary quite a bit. And indeed, you should really think that if you have a problem which is not just predict the next symbol, and I have 10 possible symbols, and so I just need to predict 10 numbers between 0 and 1 that add up to 1. But I'm doing something more complicated. I don't think it's obvious how to do it. And indeed, that's a big choice that you have to make. Of course, the loss function you choose will impact your optimization quite a bit.
Okay. Thank you.
Mm-hmm.
So Boris, I have a question about the relationship between statistical methods and machine learning. If you have noisy data, signal plus noise, if you look at the data, you can sort of guess whether it's worth analyzing the data if you have enough data to extract the signal. But can you do the same for machine learning? Can you say, oh, I have enough data or enough to extract a signal using neural networks? Is there any?
Yeah, so that's an interesting question. I alluded to it a little bit, and it's something that's poorly understood. So the way I would say it is that at the moment, neural networks typically require a very large amount of data. Okay. The kind of strange realization people have come to is that it's impossible to have too much data or too many parameters, roughly speaking. Just whatever your compute and data budget is, you should just maximize it. And of course, that's very unsatisfying because your question in part is, well, how much data is the minimal I need to solve my problem? Of course, that's very relevant. And yeah, we don't know. We're not sure, in part because we're not sure what it means often to solve the problem, quote unquote. If you're making a self-driving car, how do you know that you've solved the problem? Well, there's not necessarily a great metric. You have a brave soul drive around in it, and hopefully you don't crash into a boulder. So it's, yeah. I don't know how to answer it, and if it would be nice to have a framework for answering it, but this kind of issue of data sparse applications of neural networks and in general, being as efficient as possible has of course garnered a lot of attention, and there are a lot of interesting papers about it, but we don't have a nice, clean interpretation of what's going on.
Okay, a couple of more questions. One is a quick one. What's the software you're using for the Blackboard?
It's called GoodNotes.
GoodNotes, okay. A final question is philosophical. You mentioned that you could use a different function, the nonlinear function, instead of the simple ReLU function. Suppose someone came up with something that's quite different, but all of these heuristic or empirical insights still hold.
Well, it's hard to say. It's hard to say, At the moment, a lot of them are insensitive to the particular choice of nonlinear function. The most popular ones are, let's say, something like hyperbolic tangent roughly and ReLU. Those are things that look like a sigmoid, that asymptote, let's say, to -1 and 1 or to 0 and 1 at plus and minus infinity and kind of smoothly interpolate, or this kind of piecewise linear function. And that deeper is better, and that when you're very over-parameterized, you don't have to worry about overfitting, seems to hold for both. Okay, so that kind of very high-level empirical thing. But, you know, if you came up with a new activation function, it might have new properties, you know, and you might find that actually, I don't know, you should choose a different learning rate, or you should choose a different batch size, or you need less data. I don't know. I mean, I'm just making it up, but I think it's very unclear.
Thank you.
Mm-hmm.
Any other questions? We are 10 minutes past the hour. There's a lot of good discussions.
Dr. Hanin, I have one question.
Uh-huh.
Hello. Oh, yeah, I'm speaking. Oh, okay, good. No, yeah. I noticed that, you know, this is a tutorial thing, and I'm just begin learning things like this, deep learning. I mean, I noticed that, yeah, people from different backgrounds, yeah, are studying this. I come from the math department, just like you. I mean, what do you think is the strength and weakness for a mathematician to study this?
Well, okay. I mean, I think I can answer that to some extent. You know, from my point of view, the strength is that the common conception is that neural networks are impossible to analyze. They seem hopeless, this kind of composition of nonlinear functions. But the fact is that they have very simple and kind of beautiful principles just waiting to be uncovered. And that they're related to really beautiful mathematics. You know, I've written papers about neural networks that use everything from random matrix theory to, you know, combinatorics like hyperplane arrangements, to geometric analysis, to, you know, all kinds of other things in mathematical physics, things like the Weingarten calculus, you know, for integration over kind of matrix groups. So somehow what I find is that when I start with a practical question about neural networks, the subject is rich enough that it usually gives rise to questions about interesting mathematics. So I think that's a strength, you know, and that's a good thing. And then, but the weakness is that there are very few mathematicians at the moment working on neural networks. And as a result, it is actually not that easy to figure out what the mathematical problems are. You know, the papers that are typically written on the subject are just not written in a mathematical style. And so you know, you have to be somebody who enjoys the process of thinking about the practical kind of slightly dirty stuff and abstracting away a nice problem. So I'd say that's one of the big downsides.
Yeah, that is. Yeah, it's not very. Yeah, it's not very. Yeah, mathematicians usually don't feel familiar at first sight about the content.
Exactly.
Hey, Boris, following up on Saravanan point about noise to signal, I read somewhere that the information bottlenecks theory that was originally introduced in 1999 or so can explain the black box of deep learning. Is that, to what extent is that true?
So, okay, let me say something about that. So there was a paper that garnered a lot of attention called, a series of papers really, you know, using information theory to open the black box of neural networks or something like that. And indeed, they tried to use the information bottleneck principle to explain how neural network optimization works. Sorry for the scrolling. And they had these kind of beautiful numerics that seem to suggest that, you know, there's, in the information plane, you have this kind of beautiful dynamics. And those papers largely turned out not to generalize. You know, they happened to choose a model where they found that it worked. But what I would say is that information bottleneck has been largely a failure at explaining how neural networks work. Certainly some of the ideas are very relevant. You know, people indeed use things like autoencoders or other kinds of neural network architectures in which there's an attempt somehow to do something like compute an approximate sufficient statistic for your target labels, you know, given your inputs. And that has a very IB feel to it. But as far as any theorem, for sure there's nothing like that. And even empirically, it just seems like the story is much more complicated. You know, it's not clear how information theoretically to characterize what neural networks are doing. A lot of attempts have been made, and I don't think any of them have been truly successful.
Thank you.
Yeah.
Any other questions? Well, I think we probably come to an end to the tutorial. And Boris, I really enjoyed your tutorial and all the discussion. And there's a lot of good insight. So thank you very much for doing this for us. I think this concludes our tutorial, and we're going to make the recording available afterwards on the TAMIDS website. Thank you very much.